The smallest number that cannot be described in 20 words. Why has this one sentence bewitched mathematics for 100 years? Today we chase it all the way down. First, the introduction. There are no scary formulas today. No integrals, no matrices. We need exactly two tools: counting how many, and a sharp eye for what happens when words point at themselves. First, let's read one sentence slowly. Nothing looks wrong. If some numbers can't fit into 20 words, then exactly one of them must be the smallest. But now take that very phrase and count its words one by one. The smallest number. That. Count them all. Exactly 10 words, well short of 20. Which means we have just described in only 10 words the very number that cannot be described in 20 words. This little vertigo is today's protagonist, Berry's paradox. It's a cousin of this sentence is false, but sneakier. It shows up respectably dressed in numbers and counting. We interrogate this one sentence to the very end, and at the end we meet a limit no computer can cross. Chapter 1. A letter from a librarian. This paradox has a surprisingly human backstory. In the early 1900s, Berry, a librarian at Oxford's Bodleian Library, mailed a riddle to the logician Bertrand Russell. Russell first put it into print in 1906, and in a footnote to his 1908 paper he honestly wrote this: "It's the moment a librarian's name was etched into the history of mathematics." Russell's formal version, written in 1908, goes like this: "The least integer not nameable in fewer than 19 syllables." But this phrase is itself exactly 18 syllables. Words have become syllables, yet the skeleton is the very same trap. Russell went one step further and wrote down the number itself, 111,777. The value itself doesn't matter. The real question is this: does such a number even exist in the first place? Chapter 2. When you meet a paradox, the very first thing to question is its premise. Could it be that every number somehow squeezes into 20 words, so no such number exists at all? No. Such a number must exist, and to see it counting is all you need. The single word million names 1 million, and the single word Google names a 1 followed by 100 zeros. That is exactly what describe means in Berry's sentence, stringing words together to pinpoint that number. Now we count. With a vocabulary of about 1,000 common words, there are at most 1,000 one-word descriptions, and 1,000 times 1,000 two-word ones. With 20 words, that's at most 1,000 multiplied by itself 20 times, about 10 to the 60th. Astronomical but crucially finite. The chart on the left shows the actual scale. Allow more words, and the number of possible phrases explodes frighteningly fast. At 60 words, about 10 to the 180th, beyond even the number of atoms in the universe, about 10 to the 80th, and still finite. But the numbers? 1, 2, 3, they go on forever. There is no end. Enter the pigeonhole principle. Finitely many labels, infinitely many numbers, so some numbers must be left without a label. The chart on the right is the clincher. We shrank the world on purpose. Just 2 symbols and names of length at most 4. In this world, the distinct names you can ever form total exactly 30. The numbers march on endlessly along the blue line, so by the 31st number at the latest, a nameless number must appear. Scale it up to 1,000 words and a budget of 20, and the 30 merely becomes 10 to the 60th. The story doesn't change. Among the nameless numbers, exactly 1 is the smallest. That number is Berry's number. The premise is sound. The number really exists. So who's the culprit? It hides in how we point at the number. Chapter 3. The anatomy of the trap. Instead of squishy everyday language, let's build a toy language with razor-sharp rules. The rules. The only numeral is 1. The only operations plus and times. A description's length is the number of ones you write. You build 6 as 1 plus 1 times 1 plus 1 plus 1. That uses 5 ones, so the length is 5. Adding up 6 ones also makes 6, but that's length 6 longer. We only ever care about the shortest description. This minimum number of ones is a quantity mathematicians actually study. It even has a name: integer complexity. In this language, Berry's sentence isn't vague at all. Can be built is razor sharp, so we can simply search by computer. So I searched. Each bar is the minimum number of ones needed to build that number. The orange dashed line is the budget. 11 ones. The first red bar to punch through that line is 41. With 11 or fewer ones, no matter how cleverly you combine them, you cannot make 41. And there was no contradiction anywhere. Hold on. We just called that number the smallest number you can't build with 11 ones. Is the dizziness flaring up again? No. Keep raising the budget and plotting, and each budget quietly picks out exactly one berry number. The smallest number you can't build with 5 ones is 7. With 8 it's 17, with 11 it's 41, with 14 it's 89. The numbers leap ahead, yet the pointing sentence stays one line long. In everyday language, that very power becomes the paradox's trigger. So why is it safe here? Because that sentence is plain English, not the toy language made of 1 plus and times. That 41 is long in the toy language and short in plain English. Those two facts never collide. Measure a height in centimeters and you get 173. In inches, 68. That's no contradiction, and this is exactly the same. We laid values from different rulers side by side and gasped. A contradiction. That was the whole of the dizziness. Then why was the sentence in the introduction contradictory? Because the describing language and the described language were both English. The words being counted are English words, and the sentence doing the describing is an English sentence. The ruler had begun to measure itself. Keep the describing language and the described language separate, as in the toy language, and the paradox vanishes cleanly. This is no dodge. It's the genuine conclusion 20th century logic arrived at. We'll meet it again in Chapter 5. But before that, one more shocking fact this toy language reveals. 41 is only the tip of the iceberg. Chapter 4. The tip of the iceberg. Chapter 2's counting argument was in fact saying something far stronger. With finitely many labels, the numbers that get 1 are a speck of the whole. Barry's number was merely the first peak in an ocean of the nameless. This length of the shortest description is Kolmogorov complexity, the length of the shortest program that produces the object. We can't compute it exactly, but the length a compressor squeezes things down to works as an estimate. We compress 4 numbers of identical length, 1,200 bits each. The all zeros number and the regular repeats collapse to 96 bits in an instant, palm-sized. That means they have short names. The random number came out at 1,288 bits. It actually grew. With no pattern to exploit, its own digits are its shortest description. The chart on the right is the heart of this chapter, and it's really Chapter 2's counting argument back in a new costume. Among n-bit numbers, the fraction that shrinks by c bits or more is at most 2 to the minus c, because short bit strings are scarce. So half of all numbers can't be squeezed by even 1 bit, and 99.9% can't shed even 10 bits. Numbers with short names are the rare exception. The nameless ones never even cross your mind in the first place. One thing to flag honestly, compressors only see statistical patterns. The classic counterexample is pi. Pi's digits won't compress, but a short program, compute pi and print the digits, is all it takes. Compression success is proof that a short name exists. Failure to compress guarantees nothing about having no name. Now one step further. Kolmogorov complexity cannot be computed, and the proof is Barry's paradox itself. If a program could compute k, you could write a program that says, find the first number whose complexity exceeds n. But the length of this program is only about log n, the cost of writing n down, plus a constant, far shorter than n. So this short program describes, in fewer than n bits, a number whose complexity exceeds n. Contradiction. There is only one way out. The initial assumption was wrong. The length of the shortest description cannot be computed, not even by a computer. The moment describable becomes printable by a short program, the wordplay hardens into a full-fledged theorem. In the 1970s, Chaitin showed it. Every system has a limit L, and that any specific number is more complex than L cannot even be proven. The bridge is Gödel numbering, from Gödel in 1931. Encode sentences as numbers and a mirror appears. Formulas about numbers become verdicts about sentences. In 1989, George Bellows used Barry's paradox to prove Gödel's first incompleteness theorem anew, in just 2 pages. Any sufficiently strong system contains statements that are true but unprovable. A librarian's wordplay grew into that proof. Chapter 5. Barry's paradox is not alone. It belongs to a family, words that point at themselves. The eldest is the liar paradox. If it's true, it's false. If it's false, it's true, circling in place forever. The Grelling-Nelson paradox. Long is not a long word. It doesn't fit itself. So does the phrase does not fit itself fit itself? Richard's paradox from 1905. Take the list of all decimals definable in words, then use the diagonal argument to define, in words, a number missing from the list. The smallest uninteresting number becomes interesting by that very fact. Swap interesting for describable in few words and you get Barry. The youngest. A program bites itself. Turing's halting problem from 1936. The proof that no universal verdict program can exist. Feed a program that acts exactly opposite to the checker's verdict into itself, and the checker can answer neither way. The common thread is one, trouble breaks out when a judgment tries to evaluate itself inside the very system it belongs to. In the 1930s, Tarski nailed this prescription down as a theorem. A language cannot fully speak about itself. Chapter 6, the finale. Let's return to that very first sentence. The smallest number that cannot be described in 20 words. Such a number really exists. The contradiction came from how we pointed at it, and the cure is separating the ruler from what it measures. That's all of today. Counting how many and asking which language a sentence belongs to. Those two alone drew all of this up from the well. Barry's paradox is beautiful because it looks like wordplay, yet strikes precisely at the most sensitive nerve of language and number. Next time you hear "oh" that can be defined in a single phrase, ask back, is this yardstick by any chance measuring itself? That one question turns a dizzying paradox into calm arithmetic. The very arithmetic a librarian discovered on letter paper some 100 years ago. If you enjoyed today's journey, support us with a like and subscribe. See you at ELLS Lab for the next Odyssey.